Hello and welcome to this webinar presented by HSB and ATC. My name is Matthew and I will be your GlobalSpec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's webinar. Just to the right of the main presentation window is the speaker bio window with background information on today's presenter. And just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. And now I would like to introduce today's presenters. With us today, we have Jay Watapilli, the Vice President of HSB Codes and Standards, and we also have Jeff Henry, the President and co-owner of ATC. To read more about our presenters, please look at the speaker bio window right next to the main presentation window. And guys, welcome to today's event. And with that, I will pass things along to you to get started.
Thank you, Matt. So folks, thank you so much for joining. We're so glad that you're here. I'm Jay, and with me, my colleague Jeff. We will take about 45 minutes or so to walk you through this, and we'll try to save some time towards the end for any questions that you might have. We will be taking turns, so that way you're not stuck with my lovely face. You'll have variety. Essentially, this webinar is about an industry challenge that we're currently facing, which is the premature failures of B16.9Ts. So 3 takeaways. We will explain what is happening. Then we will get into a bit of a instructional session on why this is happening, some possible causes. And then Jeff will wrap it up with some options that we have to face these challenges. So I have been following these failures myself, at least for last 1 year. These are essentially failures of Form Ts, and there have been multiple failures in multiple units here in the US. So EPRI, Electric Power Research Institute, they published an alert last year. And since then, they have also done an outstanding job of compiling all of the failures that are reported to them. EPRI also has a program in place to study these failures in detail. So if any of you are interested in becoming a part of that program, you should contact EPRI. I wanted to kick off the webinar with a couple of statements. So there are different possible T combinations that we can think of in a boiler system. So the Ts that we're going to focus during this webinar are designed and fabricated in accordance with B16.9 standard. Now, an interesting observation about these Ts, when you look at one of these Ts, and then think about how these Ts are fabricated or formed. It's in fact quite a complex blacksmithing operation, especially when you think about some areas within that T, like crotch, as an example. It's absolutely mission critical to keep some geometry and thickness very consistent when you make them. So that would become quite apparent as we get further into the discussion. Due acknowledgement to EPRI for making this slide available to us. So this is basically a snapshot of those reported failures, a part of that database that EPRI is maintaining. So we can see that there are several Ts reported here, mostly grade 92 and grade 91 materials. EPRI is looking into a host of variety of different things in detail, like the design conditions for these Ts, the location of failures, the hours that these Ts are failing, which is, again, an interesting observation when you look at the operating hours. They're not even reaching 100,000 hours, which is typically 1/3 of the boiler life if everything is in an ideal situation. So They made a presentation at the ASME Code Week last year in November, and these are the numbers in terms of what are known to EPRI in terms of the plants, affected teas, the number of cracks. And since that time, at least I've been made aware of 2-3 failures through ATC. So, as I said, under the rubric of T intersections, you can have 2-3 different combinations that are commonly used in the boiler system. So this sketch that I have here, this is an example of a B16.9T. I want you to pay attention to this run extension beyond this tangent line from the crotch. I also wanted to point out the branch length here. And then also take a look at the picture. The picture is a B16.9T that meets the dimensional requirements of that standard. You can see that there's not a whole lot of run extension and branch length that we have here to work with. So why do I talk about that? Well, later during the presentation, we will get into some of the design aspects of these Ts. And especially during that time, I want you to remember this point I made about the shorter run length as well as the branch length that you can see on these B16.9Ts. These are some examples of other types of T intersections that you can see in boiler systems. So here's a welderlet attached to a pipe. You also have the possibility to attach a pipe instead of the welderlet. Ts also can be machined from a forged block that would look like that. It is also common to use the lateral sometimes in boiler systems. So these other combinations are interesting topics. They have their own unique challenges, and we will not get into those during this presentation. So our partner ATC got a very interesting case study that led them to really look deeper into the T investigation. So Jeff, if you're ready, take it away.
All right, thank you very much, Jay. Yes, this is not a picture of a T, quite obviously. And obvious question is, why would we start with this? Well, two primary reasons. First of all, it was as a result of some assistance we were providing to the utility that had these problems in replacing this steam chest that we were on site when the first T failure occurred. And so we were in a preferred position to assist with that damage. But the second and probably more significant issue here is that the problem with this steam chest was that the utility had begun having problems with the operation of the valves. And we ultimately realized that the reason for this problem was the fact that this steam chest, which was supposed to have been a chrome moly beam material, had been fabricated from the wrong material. And this points up a very critical issue in our industry right now. The old adage, which many of you will have heard, that you get what you inspect and not what you expect, is probably, has never been more true than it is these days. And so while Jay is going to talk in just a little while about some of the design related issues that are really undergirding this whole problem with the Ts, always keep in mind that there are other potential quality related issues that may be coming into play and that may be a significant influence in determining exactly when these Ts are going to fail. Okay. Let's see here. While we were assisting with the problem with the steam chest, as I said, the utility had a failure on one of their units. There are two sister units at this particular plant. These are supercriticals, coal-fired supercritical plants units. And while they were there, they had a failure in a 20-inch T. Now, what we're going to look at in a little more detail as part of this presentation is a 10-inch T. But this 10-inch T had a damage profile that was essentially identical to the damage profile that was also present in the 20-inch T. And unfortunately, and we're not sure exactly why this happened, but the arrows have been displaced in our presentation, so I'm going to have to override those. And there were three primary areas of damage that had shown up in this T. The first one, which hopefully you can see from my arrow, was at the center of the crotch position. And at this position on the T, there was a longitudinal crack oriented, it was located in the center of the crotch area longitudinally. There was a small, at the point of the leak, there was a small extension of this crack on the OD surface, but on the ID surface, the crack extended and through the girth weld for the branch and all the way to and through the girth weld for the run. So a very long extension on the ID surface and had obviously had broken through then to the OD surface to create the leak. Excuse me, I'm going to go back for just a minute. I forgot to mention. I said that you had the longitudinal crack at the crotch position. There were two other cracks present, and they were located at these two locations on the T side of the girth welds for the branch and the run, and they extended circumferentially as opposed to the longitudinal crack in the crotch position. Now, these two cracks were right at the edge of the heat effect, or in the heat affected zones at the edge of the welds, which is not surprising. These were specified to be grade 91 Ts. There was something a little peculiar about the crack profile in both cases, though, which is directly related to some of the design-related issues that Jay will talk about later. And that's the fact that normally when you see a crack that propagates through in a relatively thick wall component, propagates through for a good percentage of the wall thickness, there'll be a proportionality between the extent of the crack on the OD surface, if it's starting from the OD, versus the depth of penetration. And that relationship didn't hold in this particular case, because what we saw was that the crack extension at the OD surface where the crack had initiated was much more confined and concentrated within this, what you would consider to be the influence area of this crotch position. And again, Jay will give a little more insight into exactly why that's the case later on, but just be mindful of the fact that the damage profile was not what you typically see, say for a normal crack of the girth weld as a result of bending stresses at the weld. Look now at the ID surface of the T, and there's some interesting features here as well. First of all, you can clearly see the crack, and as I said, that crack ran from and through both of the girth welds, so it was fairly long extent on the ID surface. You'll notice also, and follow the arrows, there's an unusual profile right in the center of the area where the crack is developed. Now, we think that the reason for this, and this is something that EPRI also has drawn attention to on some of the Ts that they've looked at, and we think that the reason for this is related to the manufacturing process. I had the good fortune of working for many years at the old combustion engineering, which ultimately became Alstom, and then finally GE. But we made these types of Ts at the Chattanooga facility, the manufacturing facility, and I worked with the T forming operation on a number of occasions, and it was not uncommon because of the very complex metal flow associated with the fabrication of these Ts that you would end up with a fold-like defect right in the center of the crotch position. And recognizing that, we would look for that after the T was produced, and if a fold did exist, then that would be ground out. And we suspect that the reason you're seeing this rather unique feature on the ID surface of these Ts is in response to the presence of one of these defects, which the manufacturer was at least astute enough to eliminate. The problem is, of course, that by eliminating that defect, you've now reduced even further the wall thickness in an area that, as Jay will explain, is particularly critical. We looked at the wall thickness, and of course, there's at least one interpretation of the rules of B16.9 is that you can determine what the minimum thickness for the T should be based on a simple cylinder. On that basis, if you look at the design conditions, that would indicate a minimum wall thickness for the T of 44 millimeters. Again, I apologize, the figures for some reason have been displaced, but what this is showing is that if you look at the center of the crotch position, that turned out to be the thinnest wall of anywhere on that T. And in fact, it was right at the minimum required by the simple cylinder calculation. We did find even thinner wall thicknesses right at the edge of the weld, but because of the orientation, that didn't have quite the same significance as the thin wall in the crotch position. Of course, we did a complete destructive examination on this T, and as part of that, we did a chemical analysis using optical emission spectrometry. And what we found is that the T was not grade 91 at all. In fact, we don't know what it is. It doesn't conform to any known grade that at least that we're aware of. Certainly nothing in the ASME boiler pressure vessel code. When we first saw this, we thought, okay, here's the problem. We had a rogue producer that produced a number of these Ts with the wrong material. They had poor creep strength, and so they're failing early. But when we looked at the 20-inch T, the original failure, and did the chemical analysis, that T, which had exactly the same damage pattern as this 10-inch T, in that case, the chemistry did conform to the requirements of grade 91. And so while this highlights the problem, the potential problem with quality control on these Ts, that can't be considered to be the root cause of this particular problem. And there'll be more on that later. With that, I'll turn this over to Jay, and we'll talk a little bit about the absence of MTRs for these Ts.
Thank you, Jeff, again. So the discussion about the chemistry was of interest to me when I talked to Jeff about this earlier. In fact, he was looking for an MTR for this T, and that was not something he could get from the OEM. So that just made me curious in terms of reviewing some of the requirements that we have in Section 1, and I'll talk about B31.1 in a minute. This pertains to boiler systems, so we should be looking at both. But within Section 1, we have a paragraph PG11, and that's where usually we handle standard pressure parts like these Ts. So within PG11, there are paragraphs that talk about components that are made to an ASME standard and then non-ASME standard. So PG11.3 is where ASME standard pressure parts are addressed. If you look at the subparagraph PG11.3.6, it tells you that inspection, MTRs, manufacturer's partial data reports are not required for these components. So that's an interesting comment there, because when you look at the material specification, like for example, SA 234, by the way, B16.9 has several material standards that are listed where you can possibly bring a fitting that complies with B16. So I took SA 234 as an example. If you look at that specification, it is requiring you to obtain MTRs. But when you have a situation like this, like a construction code book having a requirement different than a reference code book, which is Section 2 in this case, usually the construction code book would be on the driver's seat. I wanted to point out that B16.9 indeed has marking requirements. So typically these Ts are marked. And that's all we basically need as a minimum code requirement to make those Ts acceptable under Section 1 rules. So here we have the marking requirements from B16.9. I'll take a minute or two to briefly look at B31.1 standard. So there are at least 2-3 paragraphs that I can think of, like this one, 106.1, that talks about fittings. Then we have 104.7 that talks about other pressure containing components. There's this paragraph here that talks about how to establish the PT ratings. But what is common in all of these paragraphs is this reference made to table 126.1-1. And that is the table where B16.9 standard is listed. So basically, as long as you bring fitting in accordance with the standard listed in this table, that would be acceptable for B31.1 applications. Boiler external piping in B31.1 is of interest to us. It talks about both BEP and non-BEP, but I was just curious to take a look at the BEP section. So within this paragraph here, 123.2.2, there's a subparagraph C that tells that you can use Section 1 materials for BEP applications. So again, that's an interesting information because typically OEMs that make boilers would also do piping work, and it could go the other way. And then when you have multiple things going on, it's not uncommon to have one quality control system to address both construction activities or somehow unify it. So as long as these materials are used with the allowable stresses from Section 2, Part D, Tables 1A and 1B, and meeting some of these Section 1 paragraphs like PG 5 through PG 13, those materials would be acceptable for B31.1 applications as well. The last thing I want to point out is an interpretation. This was published back in 1979. So I would read the question one. May flanges and pipe fittings made of materials conforming to ASTM specifications produced and identified in accordance with B16.5, 16.9, and 11 be used for BEP? The answer is yes. As long as PG11 requirements are met, they can be used. And I showed you those PG11 requirements a minute ago. Question two, again, is a validation of the statement I made about MTRs. If these components are used as provided for above, or certified test reports or additional inspection required? The answer to that is no, they're not required, provided PG11 requirements are met. So this, again, confirms the minimum code rules that I just mentioned. We got a couple of pictures, and I think, Jeff, you may want to comment on these, so I'll give it back to you.
Okay, thank you. And one of the questions that will have come up by this point, as you've been following along, is okay, we know that the problem exists in the tees, and what's the primary damage mechanism? Why are these tees failing? Is it because of flaws? Is it because of manufacturing-related flaws? Is it because of fatigue damage? Well, as part of the destructive examination on this 10-inch tee and confirmed by other examinations, what we're finding is that in both cases, both in terms of the longitudinal crack at the center of the crotch position, and also in terms of the circumferential cracks that are developing at the girth welds, that in all cases, the cracking is creep-driven. It is creep-dominated damage that's forming in these areas in response to the operating conditions. Now, this is surprising for a couple of different reasons. But the primary one is that, as Jay indicated, although ASME doesn't identify a design life for any of their systems, when you look at the way the allowable stress values are calculated for these materials and look at the factoring involved on the various test data that has to be supplied in order to calculate the allowable stress values, if you follow through on the mathematics, that even if you have the worst possible material properties, you should have a minimum life somewhere in the range of 250 to 300,000 hours. And yet, as Jay showed earlier, these failures are occurring in fractions of that particular time. And then Jay is going to talk a little bit more about exactly why that's coming, but we did want to demonstrate just the nature of the damage. This is showing the damage at the girth welds. You can see in this case that the cracking has initiated at the OD surface and is propagating along the outer edge of the heat affected zone in the grade in this particular material, the so-called type 4 region. Go back just for a moment to this slide, on this particular crack, which is a longitudinal crack running along the center of the crotch position, when we looked at the pattern of secondary damage that developed here, and with creep failures of this type, you always have some secondary damage that develops. When we looked at the pattern of that damage, what was clear was that this cracking was actually starting subsurface, relatively close to the ID surface it appeared. It then propagated through to the ID, and only as the last step in the process, propagated through to the OD surface. That has important implications for inspection, obviously. So with that explanation, I will, well, this is just a little bit more information about the T failures. And the one thing to point out here, with the kind of issues that we saw with these Ts, wrong chemistry in some cases, but not all cases, some of the design deficiencies that Jay will explain, wanted to emphasize the fact that these were not supplied by one of the OEMs at the so-called second or third tier suppliers. These were the product of an OEM that would be considered one of the premier OEMs in the world. So again, highlighting the potential issues associated with quality. But with that, I'll turn it back over to Jay.
Thank you, Jeff. At this point, I would like to take a look at the design aspects of these Ts, and in conjunction with the comments Jeff made about the failure locations, I think it's important to examine how these Ts are designed. So I'll start with section 1. I don't have a slide on E31.1, but I'll verbally report what I have to say. But let's look at section 1. So in PG42, under paragraph reference PG42.1, we have this node. And this node is telling me as a designer that I have to essentially treat these fittings as straight seamless pipe. And they also make reference to this paragraph 2.1 from B16.9. So I have that paragraph listed so we could look at it. Again, same verbiage consistent with that note, that you would take one of these fittings, not just the T, but any fittings that are contained within that B16.9 standard, you would essentially treat them as a straight seamless pipe. Now, just to close the loop here with B31.1, as I showed you earlier, those paragraph references are making reference to the table 126.1-1, and B16.9 is listed. So from there, you would go to the B16.9 standard and then follow the standard in terms of how to establish the PT ratings of a B16.9T. Now, I wanted to take a moment to kind of explain, when I look at that T, I've done a little bit of design calculation. So truth be told, I don't see a straight seamless pipe when I look at that T. In reality, what you see in that T is not just the run pipe alone, but there's an opening on it, right? So from mechanics, I know that when I have a cylinder where I have made an opening, and if that cylinder is under internal pressure, right adjacent to that opening, you will have stresses that are significantly more than the average hoop stress or membrane stress. That is just the way the openings really work. But the good news is that as you move away from that opening, the stresses will attenuate to an average membrane stress, and you can see that here. If you're wondering what these two sketches are, one is for a cylinder, the other one is for a sphere. So you can ignore this one for now. So let's go back to some of the comments that Jeff made. At the beginning, I also said that that very short run extension is a critical thing for the T. So as you think about it, if you look at that stress pattern, the location of the crotch is right at the edge of that opening, where you can see a predominant high stress as a result of that opening. Past that edge, you will have, typically, if you compare this figure with the T, you would have the run extension past that opening, and then that's where the stresses will actually take its way to attenuate to a membrane stress. So that length is a critical information or component when it comes to how these stresses are sort of normalized as you move away from that opening. Again, we have just provided like a FEA plot just to compare that. If you take the time to make an FEA model with an opening, you can see consistent stress pattern right around that opening. So the fact that we have a crotch where a lot of cracks are happening consistently in these teeth that are failing, this stress pattern in that location is a very important information. Now, in the this slide and the next few slides that I'm showing are purely an academic exercise that I did. So if you were to think of reinforcing an opening, if you were to design a T on your own, you would go to section 1, and we have rules for that. We have a figure PG 33.1 that really condenses all of the information you need to reinforce that opening. So for the sake of simplicity, I have taken a shell and a nozzle intersection, and then essentially when there's an opening, section 1 requires the opening to be compensated in all planes. But typically, in the case of a cylinder, the plane that would get under consideration would be the plane that goes through the longitudinal axis of the run pipe, because that's the plane where the hoop stress is acting normal to that plane. So if you take a plane like that and project it on a 2D plane, you will get a sketch like this. And essentially, this is what is provided in section 1. Of course, we made it a little complicated by giving more details. But you can see that when the opening is made, that's the area where the arrow is pointing out. That's the area that is lost as a result of that opening. We then have a limit of reinforcement that we have established within section 1. Remember that discussion I had in the previous slide where the stresses will attenuate after a certain length. So this limit is consistent with that. So the code has established a maximum limit. From that limit, you would count the extra thickness you can count towards compensating for that opening. So you'll get a little bit from the shell, depending on the shell thickness or the run pipe thickness. You will then count the available area from the nozzle. And if they add up to the area that you lost, then the opening is reinforced. If not, then we need to figure out where the extra area is going to come from. So as an example, you can add a repad. You could count the well areas that are within that limits. If there's a nozzle that is projecting inside, you can add that, and all of that would add up to the area that you need. So that's, in a nutshell, this discussion I had has nothing to do with the T failure, but I was just taking the time to bring some relevance to this in the context of the T that we will see in a minute, whether that's properly reinforced or not. So for what it is worth, I decided to take a B16.9 T, which is 16 by 14 reducing T. That means that the run diameter is 16 and the branch diameter is 14, the OD. These dimensions that I have listed, they come straight out of B16.9. So this particular one had some creep damage. So essentially, I would call that as a T that failed or showed some symptoms of some premature defects. I happen to have the design and the pressure and temperature, the design conditions. So I have listed those here. 2,630 PSI is the design pressure. The temperature is 1105 degree Fahrenheit. The main run thickness for this T was more than 2 inches. The thickness of the branch was close to 1.78. So in order to meet the section 1 minimum rules, I need to treat this T as a straight seamless pipe and do those calculations. And because I have a different diameter between the run length and the branch length for this T, I have to have 2 sets of calculations. These equations, by the way, come from PG 27. And I calculated the thickness that I need for the run as well as for the branch. And these thicknesses, in reality, will be less than what I have here for the run as well as for the branch. So this basically tells me that this T would meet the minimum Section 1 requirements. And by the way, this is SA 234 WP91. So again, out of curiosity, as a simple academic exercise, I took this T to see if how would this compare when I do a reinforcement calculation in accordance with Section 1. So the area required, remember that area that I showed you 2 slides ago that I need to compensate, that area I calculated around 19 square inches. And then I have 2 sets of equations to calculate the available area that I can get from the shell. But in reality, what is happening here is that, of course, these equations have assumed that I would have a certain reinforcement limit. But in reality, that the T supplied in accordance with B16.9 has these dimensional requirements. And so I have called out the run extension in this particular case, which is only 5 inches. Now that 5 inches is comparing to the code required limits, which is the higher of these two, 10 and 7. So in reality, for this T, I only have half of what the code would require. Now, when you think about it, some of you may have done calculations, and this is often a topic that comes up. The code would establish the maximum limit. What if I don't have that? Especially when you have overlapping reinforcement. So of course, you don't have to have this, but if you don't have it, something has to be offset there to really maintain that required area. So one way to do that would be to, if you have to reduce that limit, you would find other ways to compensate for that reduction by either increasing the thickness or maybe add a branch with more thickness or add a repad. But in the case of T, you got to work with the run extra thickness as well as the branch extra thickness. So lo and behold, if I adjust these equations based on what I have for this T, you can see that the available area is further reduced from 2.6 to almost half of it, 1.3. A similar story when it comes to the area available from the nozzle wall. Again, the extension here is about 4 inches. I would need to compare that with the code required extensions in terms of the limits. In this particular case, I have to take the minimum of these two numbers. So that would be 4.4 comparing with 4. So similar adjustment or modification that I need to make for the available area from the nozzle wall. And if I do that, my A2, which is the area available from the nozzle wall, is further reduced to 1.8 approximately. So going back with this area, about 1.8 square inches from the nozzle wall, adding up to this 1.3 that I get from the run pipe, you're nowhere close to the required area. So that's an observation I wanted to make. But again, Section 1 doesn't require this T to be designed in accordance with Section 1 compensation rules. I mean, I could have picked up B31.1 compensation calculations, but they're essentially similar requirements. So that being said, I know that at least there's one other method that I could look into, which is the pressure area method. Now, in ASME boiler pressure vessel code books, the pressure area method is, I would say it's not foreign. In Section 8, Division 2, we have the pressure area method in Part 4. But what I have done here is a handbook that I happen to have. This was published by M.W. Kellogg Company back in 1961. So they published a book on piping systems. And they happen to have a convenient equation to calculate the stresses on a T to make sure that there's enough compensation. So essentially, you're looking at the pressure area, which is hatched here, comparing it with the metal area, which is this one. And by rearranging these equations, we can then calculate the actual stress that is acting on that T. So that stress in this particular case was close to 13,000 psi, and that would compare with the allowable stress that I can get from Section 2 Part D for this T, which is only 9,960 psi. So that tells me that this T would be overstressed. So the reason I brought up these two cases is that, from an engineering standpoint, how would I reinforce this T? Yes, I don't have to use the Section 1 reinforcement calculations. That's not mandatory. I don't know if Jeff mentioned this, but I know that some of the practices that are followed in some of the OEMs that I know they would make sure that there's some extra thickness in the crotch location, at least as high as 20% more than the rest of the run. And so I was trying to do a similar exercise for this B16.9T. The other observation that I wanted to make is that in the standard in B16.9, there's hardly any details provided when it comes to the inside radius that is required for the crotch thickness by itself. The only information are the run length, the branch length, the minimum thickness at the end of the T, but there's no mention about the crotch thickness or any additional information related to the reinforcement of the opening itself. I wanted to point out this paragraph from the foreword of Section 1. All of the BPV boiler pressure vessel codebook sections have this foreword. So this paragraph is of specific importance to this discussion because many times we HSB would get into providing tech support for our clients, and we get these questions that, hey, here's the nice detail, I wanted to use it, I think the code should have it, why is it not in the book? And our stock answer for all of those questions would be that, well, Section 1 doesn't have all of the necessary information in terms of replacing your education, experience, engineering judgment when it comes to designing boiler systems. So we have some minimum information related to safety, like our allowable stresses, some minimum well details and so on, but you're not going to find every single detail that you need to design a boiler properly. So I just wanted to call attention to this paragraph from the foreword. Jeff, I think we got a couple more slides where I would imagine you would take the opportunity to sort of wrap up in terms of how to address this problem.
Yeah, thank you, Jay. Before I get into the idea or the issues associated with assessment of the T's, I did want to mention a couple of other things that I failed to mention earlier. Obviously, when you see failures at a component like this in a piping system, one of the first things that would come to mind is, okay, piping system isn't properly supported, these T's are too heavily loaded, and that's what's going on here. I can't obviously speak for all the failures that have occurred, but in the where we've had an opportunity to look at this is one of the first things we did evaluate. And in the situation for the plant that had the multiple failures, we know for a fact that these were not related to problems with piping support or excessive system loads on these T's. The second thing I want to point out too is that in this case, these units are not heavily cycled. So this again is not a situation where it's related to rapid ramping up and down of the units multiple times over the course of the year. So keep that in mind, particularly in relation to what Jay just talked about in terms of the inherent weaknesses associated with some of these T's based on that lack of reinforcement. Now, with all that, nobody knows exactly what the total population of the T's that may be at risk out there are, although it's generally conceded the number is fairly large. So from that standpoint, questions obviously are going to come up, okay, what do I do if I'm operating a plant? What do I do to determine if I've got T's that are at risk here? And some type of assessment is going to be critical. We've had opportunities to run some of these assessments already, And some of the information that's required should be fairly obvious based on the discussion we've had so far. Obviously, dimensional measurements, and I point out wall thickness, but it's not just the wall thickness, because you also want to look at the dimensions of those extensions from the run of the branch too, because they will be critical in determining the likelihood of problems at the girth welds. Chemical analysis, although chemistry was not the primary problem in the T's we looked at, if you have a specified material and the component has not been made of that material, then that obviously introduces other potential influences on the serviceability of the T that will have to come into play when you're trying to rank the T and determine the risk of premature failure. The hardness of the T's. When you're dealing with the creep strength and transphorytic steels, then the processing of the T's, and particularly the heat treatments that have been carried out on the T, can become critical in determining what the creep resistance of that material is going to be, even if the chemistry is correct. And so the hardness, taking hardness profiles is one way of evaluating whether that processing has been done correctly, and becomes a component in assessing the likelihood of failure. And then last but certainly not least is going to be inspection itself. You want to know in a given T, has any damage initiated? If so, to what extent can you try to size that damage as an indicator of the relative proximity to failure? And so that's going to involve both surface inspection, PT or MT. As we said, for the cracking that we saw at the girth wells that had initiated the OD surface, and so the surface techniques would be very effective for there. In the case of the longitudinal cracking in the crotch position, at least for the ones that we've looked at, these clearly have started subsurface, and in those cases, volumetric inspection is going to be essential in order to determine, first of all, whether damage is present, and then using some of these advanced ultrasonic techniques in trying to come up with sizing for that damage as an indicator of the relative proximity of failure. Let's see, I think we've got a slide out of order here. All right. One other thing I mentioned, I apologize, we have a slide out of order here, but you go through an assessment process, and let's say you got a T that you want to assess, you've gone through the assessment process. Part of what is going to be involved in trying to determine the relative risk of failure for a T is going to be taking all of that information that we just look at, and if on the inspection you find no advanced damage, then you're going to look at the relative potential influence for things like the geometry. What is the wall thickness in the crotch area? Is there reinforcement in that area? You're going to look at the material composition. You'll look at the indirect evidence of the processing history based on the hardness testing. You'll also look at the operating conditions. And then in some cases, it may well be that there are system loads related to improper support of the piping system that may be additive onto an already existing weakness in the T, all of which would have to be taken into account in trying to come up with some kind of ranking in terms of the likelihood of failure for a particular T in a system. And then if you do have damage, if while doing the inspection, you do find evidence of cracking, either at the girth welds or in the crotch position, then the situation becomes, depending on the severity of the damage, can you continue to operate? If you can't continue to operate, what can be done as a measure of temporary repair in order to allow the unit to continue to operate until such time as a replacement can be obtained? And that would, based on modeling that we've looked at, we're trying to look at how could the repair be profiled in such a way that the weakened zones associated with the heat affected zones are outside of the highest stressed areas. And again, these repairs are always going to be temporary, but it could be critical in allowing a unit to continue to operate for some period of time. until replacements could be obtained. And then in terms of the replacements themselves, that based on the modeling work that's been done, it's clear what should be done in terms of replacement T in order to provide the kind of reinforcement that would eliminate the problems that we're seeing in these Ts that are failing prematurely. So with all of that, we certainly, I speak for Jay, that we very much appreciate your attention here. And if there are any questions, we'd be glad to entertain them at this time. And Matt, if you could help us with that, we'd appreciate it.
Absolutely, and thank you both for that great presentation. That was wonderful. To the audience, we're going to move into the Q&A session. We have a little less than 10 minutes to go before the webinar ends, so we're going to try to answer as many questions as we can. We already have a lot. We have a very large audience today, and we were expecting quite a bit of questions. So with that said, if we don't get to your question, if we don't have time, we will reach out after the webinar is over. We do appreciate you sending them in, and we would love for you to send more. So if anyone has any other questions or comments, now would be the time to enter that information in the Q&A box on your screen and click submit. We will receive it, and as mentioned, if we don't answer it in the next 10 minutes or so, we will reach out after the webinar is over. Okay, let's get into the questions. Okay, so our first question for today. This is directed to Jeff. You had mentioned creep failure earlier. Could you further explain that? We often hear the term, but would appreciate it if you could explain a bit more. Thank you.
Okay, sure. When we say creep failure, of course, what happens in a creep failure, and I'm not sure to what extent you want to try to get into fundamentals on creep damage, but creep damage is basically a form of damage that occurs as the result of the combined effect of temperature and stress. At elevated temperatures, when a component is put under stress, there are changes that occur in the structure of the material that end up producing damage. And that damage will ultimately manifest itself in terms of voids and discontinuities in the structure of the material. Under the temperatures and stresses that we typically see in boilers and boiler-related type systems, then the initial visible indication of creep damage when you're looking at high magnification is typically a cavity, an isolated void that tends to form along grain boundaries. As that damage progresses over time, those voids will link up. They'll form oriented cavitation along grain boundaries, ultimately microfissuring, and then in the final stages, it will occur as macrocracking, which is visible to the naked eye. Sometimes creep damage is profiled in terms of the stage of damage. So early on during the initial process of loading at elevated temperatures, you go through what's called sometimes primary creep, in which you have a balancing act between the hardening or strengthening action versus the softening and damaging action. You'll then get into a so-called stable creep mode, or secondary creep mode, in which you have a balance in between those two modes, and then ultimately go into tertiary creep, where the damage mechanisms take over and lead to the failure of the component. Again, I hope that answers the question, but creep damage is a very big and broad subject, and it would take several semesters to go through it and do it justice.
I think that was great, Jeff. Thank you for that. And thank you for that question. If you do have a follow-up, feel free to add that to the Q&A box, send it in, and we will get back to you later. Okay, let's move on to our next question. Again, to the audience, you can still send us your questions. You can add that to the Q&A box now and click submit. I also want to quickly mention there's a number of resources on your screen, including a contact us form. So we do encourage you to use that and reach out to the team if you want to continue the conversation. Okay, now for our next question. The EPRI population of failures appears to have more reducing Ts than equal Ts. Does this indicate the reducing Ts are more susceptible? Guys?
Jay, do you want to try that. I will just point out that the 10-inch T that we looked at, and we know of at least 2 of those failures that are in 10 by 10s. So it's not just the reducing Ts. But from a design aspect, Jay, do you have any comment?
No, not really, Jeff. I think I cannot, based on the information that is available to me, I cannot make a distinction between reducing Ts to be more prone to these failures compared to the equal Ts. I guess the fundamental issue, as I understand, and I'll take this moment to sort of reemphasize some of the points we discussed. So the core issue that we see is that when you think about how these Ts are reinforced and having the opportunity to look at some of the thicknesses inside, that to me is the main problem, that you have an opening that is not adequately reinforced, and as a result, these stresses will find its way to cause some premature failures. So that'll happen regardless whether it's a equal T or reducing T. The key thing is that do you have enough thickness around the crotch where the stresses will really be more than the rest of the T, how much extra thickness you have. So the answer is no. I don't think it really matters in terms of reducing Ts or equal Ts. So.
Excellent. Thanks, guys. Okay, moving along. We have a few minutes here. We're going to try to answer some more questions. We have a question here in the queue. Does the HSB and ATC team provide specific services to address this issue? And if so, how would we contact you to discuss? Before the guys answer, I just want to mention on your page, there's a form. You should be able to fill it out. It's a contact us form that will go directly to the team. You can also email webinarteam@globalspec.com if you have any questions, and we will direct you to the appropriate contact person. But the question is, guys, does the HSB and ATC team provide specific services to address the issue?
Absolutely, we will, and I'll let Jeff speak. We will make sure we provide contact details in terms of who's the right person from our team to get in touch with. Jeff, anything you want to add more?
Yeah, I would just add, in terms of the assessments, which we talked about in the last couple of slides, we've already done several of these assessments. We're learning with each one of these and refining the procedures, but we can provide all the services required in order to carry out these assessments. And so if we can be of any assistance, we'd be happy to do so.
Oh, that's great. Wonderful to hear. It's all about collaboration. All right, looks like we have time for one last question. So this seems like a good one. And again, to the audience, if we didn't get to your question, we will reach out later. You have about a minute or two to type in any last questions you may have. So if you do have any last things on your mind, now would definitely be the time to send them in. You could type it into the Q&A box on the screen and click submit. But for now, this is going to be our last question for today. Why is something so fundamental as the design of a simple pressure part not adequately addressed by the ASME B and PV and piping codes? Guys?
So I'll take a stab at it, and then Jeff, definitely feel free to embellish anything you further think appropriate. As I pointed out in the foreword, there could be many situations where we don't have enough requirements in the construction code to address every single detail that you get into. One possible situation that I can think of is that as the code book evolved by adding more rules and addressing, the state-of-the-art technology and so on and so forth, there were a lot of expertise available to a lot of the premium OEMs, at least here in the US. And as these people use their own unique ways to address these problems, and many times when we discuss these issues at the code committee, consensus cannot be reached. and therefore they did to that paragraph that I showed from the forward to provide justice to using their own engineering judgment. People have evolved using their own techniques. So when this happened, interestingly, I had interactions with some people that I can reach out to. And in fact, the reference that I made to that M.W. Kellogg handbook, that actually was published back in 1961. So I know people have used that and they have their own T designs. And as Jeff pointed out, that combustion engineering used to make their own T. So people have addressed it. And that's one reason why some rules are not in the book, because number one, there's no single way to address those things, but that comes to the engineering judgment and education and your desire to do a proper boiler design. It is expected that they use their own rules. So this is a pressing issue, and this is definitely going to take some time for the code committees to discuss. We have started that process. So it is not clear at this point where we're heading, but definitely that is something that we're actively following and discussing. Anything you want to add, Jeff?
No, I think you did a good job of explaining it, and you're exactly right. Having come from an OEM, that your description is excellent.
Excellent. Thank you, guys. And thank you for that question. I just want to, again, mention that we received so many great questions, and we do apologize we don't have time to answer them now, but either Jeff or Jay will be getting back to you guys within a few days with answers, so you can expect that. And once again, I just want to say big thanks to HSB, ATC, Jeff, and Jay. Thank you so much for the great presentation and also taking the time to answer some questions from our audience. And of course, we'd like to thank our audience members for being part of this event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you can come back and watch this again or share it with your colleagues. And lastly, if you could, please take a moment to complete a survey which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.